Hello, everyone. My name is Zhicheng He, a master student from Nanjing University, China. It's my great honor to have an opportunity to visit the University of Strathclyde as a visiting researcher from 3rd October 2016 to 31st March 2017, funded by Project GREAT. My supervisors is Professor Zoe Shipton and Dr. Yannick Kramer. My research is focused on the simulation of fluid flow in fracture. This PowerPoint is going to introduce a novel modeling method of fluid flow simulation. Here is the outline about 5 parts. Part 1, Introduction. Part 2, Aperture Measurements. Part 3, Aperture Distribution. Part 4, Fluid Flow Simulation. Part 5, Result and Conclusion. Aperture is an important parameter of fracture geometry, which affects the permeability of fracture rock mass greatly. It is significant for characterizing the inner structure and evaluating the permeability of fracture rock correctly. To obtain the information of fracture aperture accurately, however, the traditional simulation of seepage flow in fracture rock mass usually considers the fracture as a plant without any changing width value or hard to describe the realistic fracture aperture in model, which seriously affects the accuracy of the model. Therefore, in this study, a novel modeling method is proposed. The fracture image taken from microscope is processed by digital image processing technology first. Then, the fracture aperture is measured by century X the algorithm of aperture and its distribution is described. Once the probability distribution is determined, we can generate a random fracture model whose aperture follows the same probability distribution by using the Monte Carlo method for following lattice-Boltzmann method simulation study. In the final, simulated the fluid flow in both real fracture and random fracture and compare the effects of each simulation and the QB loss result. The RGB picture obtained from cameras, CT scanner, and other devices cannot use to analyze directly and need to be transformed into the binary image by digital image processing. The digital image processing adopts as a tool of processing measurements and the digital representation for the spatial distribution of different components of geomaterial has been widely applied to be internal structure quantitative analysis of rock at the model level. 4 case steps are taken in image processing on MATLAB in this study. First, image pre-processing. Second, binary segmentation. Third, fracture extraction. Fourth, fracture restoration. Several methods are proposed for fracture aperture measurement in previous researches, known as equivalent air cycle methods and minimal enclosing rectangle algorithm, and so on, shown as Figure A. The shortage of these methods is that the aperture obtained by these methods is kind of approximation of real aperture for each fracture piece, and may cause large differences compared to real aperture in some cases. Aiming at the shortage of traditional methods, according to the definition of aperture, which is the perpendicular width between the two boundaries of fracture, a new method, century axis algorithm of aperture is proposed. Schematic diagram of centric axis algorithm of aperture is shown as figure B. The fluid chart of the CAAA is shown as figure C. A boundary image of ideal fracture whose size is 500 times 340 pixels and aperture is equal to 20 pixels constantly made by image J shown as figure D was used to verify the validity and accuracy of CAAA. Meanwhile, the minimal enclosing rectangle algorithm was used to make a comparison. The results show that the centric axis algorithm of aperture is reliable and more accurate than the minimal enclosing rectangle algorithm and can be used to measure the fracture aperture in following study. Probability distribution function is often used to describe the distribution of aperture in a fracture. Take one fracture picture as an example. After aperture measurement, three distributions log normal distribution, gamma distribution, the generalized extreme value distribution, GEV, was used to fit the histogram. Then, the chi-square goodness of fit test and one sample KS test was both used to test that which one is the best. The results show that the GEV is fitting best. The latest Boltzmann method is a mesoscale computational fluid dynamics method based on the Boltzmann transport equation, whose main idea is to bridge the gap between the microscale and the macroscale by not considering each particle behavior alone, but a collection of particles as a unit. The property of the collection of particles is represented by a distribution function. Specifically, the LBM solves fluid dynamics problems through the discretization of time delta t, space delta x, and velocity ER vectors. In this, the solution domain is divided into layers that represent a small part of space delta x as well as time steps delta t associated with a tiny period of time. Each lattice contains several particle distribution functions (PDF), and each PDF contains data defining the statistical character of particles that travel at a determined point and moment in the time in a specific direction. There are different types of LBM models depending on the lattice arrangement. The D2Q9BGK LBM model was used in this study. Starting from an initial state, the configuration of particles at each time step evolves into sequential stop-steps. A. Collision, which occurs when particles arriving at a node interact and change their velocity direction according to the scattering rules, and B. Streaming, in which each particle moves to the nearest node in the direction of its velocity. The collision is a process of established local equilibrium in the lattice area, while the streaming is a process of bringing the local equilibrium into the whole solution domain. These two processes are carried out alternately at each time moment until the calculation is converged and the macroscopic results of fluid flow are obtained. According to the principle of LBM, the algorithm is programmed based on MATLAB. Lattice unions are used in all the computational process of the numerical model. Flowchart of program realization is shown as left. The planned Poisson flow is used as a test benchmark problem to test the code. The test results show that the flow field distribution simulated by LBM is consistent with the analytic solution of planned Poisson flow very well. Therefore, the validity and the accuracy of the LBM codes programmed by MATLAB is proved. Using the LBM to simulate the fluid flow in both real fracture and random fractures, the random fracture model is generated by using the Monte Carlo method, whose aperture follows a certain probability distribution after probability distribution of fracture aperture is determined. In order to avoiding the contingency, 4 random fracture models were generated. The random fracture and the simulation are shown in the table. The velocity distribution and the pressure distribution as a cross-section along the centering line of the fracture shown as the figure A and figure B. The LBM flex of fracture and the relative error of each random fracture and the cubic loss results compared to the simulation value of real fracture model are shown in figure C. We found that the flex of the fractures whose aperture follow the same probability distribution is very close. Even for the biggest relative error is no more than 5%. However, the relative error of the cubic loss results compared to the real model's results is up to 25%. Therefore, it can be seen that the distribution of fracture aperture has a significant effect on the probability of fracture. Using the stochastic model with the aperture distribution which obtained from the actual fracture in model when modeling can reflect the actual fracture seepage characteristics and can improve the simulation accuracy greatly. That's all. Thank you for your attention.